Everybody, thank you for having me. Texas Groundwater Association, thank you for having me. I'll try to make this as painless as possible. I know everybody's ready to leave. It's been a pretty good day. A lot of folks have been here. So without much ado, we'll get started. I'm Raymond Straub. I am a principal geoscientist at Straub Corporation out of Stanton. We are a groundwater consulting firm, as well as a litigation support, drilling contracting, and land and mineral company. And we're here to talk about zombie wells. Kind of a funny name, zombie wells. I didn't make it up. It's not my name. A friend of mine, he wrote a book, and that's one of the topics in his book is the word zombie wells. Me again. And the actual definition of a zombie well. Really old plugged wells that come back to life after death. In other words, wells that have been plugged. Or something, or they cease to be useful, and they come back to life. Start leaking at the surface, leaking at the subsurface, leak to the environment, become significant problems over the years. And they've been in the news here the last little bit, right? The last couple of years, we've seen a lot of these strange phenomena. Like this one right here, actually was there the day this one was discovered. Roaring to life. And I worked on this well here as well. This one has been flowing for years. For over 50 years, this well's been flowing. Small team that I put together to work on these projects. I was contacted about 5 years ago from an attorney that needed help. And she said, "Can you come help?" And I said, "Sure, let's see what we got." So for the last 5 years, we worked on a project, pretty extensive project. I've also worked on other projects like that for groundwater conservation districts, flowing wells, problem wells, leaking oil wells. I consulted in the environmental industry for 25 years, working on problem wells, subsurface leaks, cross flow, flows to surface, flows through springs. And so it was a unique challenge that led us to kind of where we are today, working on these problem wells. Yeah. I employ young scientists who are just out of school, who are fascinated by the work. They intelligent, just need an opportunity. And the work is fascinating, it's complex, nothing simple. If it's simple, we don't do it. So as you see here, zombie wells in the news. This well right here is the Estes 24, the day it sprang to life on the antenna. This well here is the one on 329 that sprang to life on Billy Meister's place. This is one of the wells flowing in Imperial, been flowing since the 50s. This is another well in Imperial that we sampled. H2S is so strong that we had to use respirators to even approach the well. This is another well that was in the news. You probably saw it in the Houston Chronicle. This is off of 329. And that's actually water from the well flowing over the rig floor. That truck is 8 or 9 feet tall to there. So that's over 12 foot to the floor. And it's still another 8 to 10 feet above the floor. That's how high the water was flowing out of the well while they were trying to work on it. This well is in Toya. And this is in Crockett County. I don't know if you can see it because of the table. But there's the oil well right there, sticking down into the collapse. It's 70 foot to the top of water from here. And whenever we actually walked up there and looked, we went around to the other side and looked, and we had been standing on an overhang that was 30 foot back in underneath us. So here we are, standing out on top of this precipice, 70 foot above a sinkhole full of water. It's like, oh, wow. We need to be more observant. So mechanisms. The anatomy of the zombie well. What makes it happen? It's pretty specific. It's pretty specific set of circumstances occurs for these zombie wells to exist. And a lot of it starts in the original design, the original concept of the well. There can be water wells, there can be oil wells. Most often, the most egregious ones are oil wells because they're deepest. But even shallow wells can be problematic. So it starts with the original design, the life cycle, what the well was originally designed for, the formations in which it penetrated, the type of concept for the expense of the original design. Most wells, for economic purposes, are designed with a finite lifespan. Cheaper is better, faster rate of return, quicker to the profit. Life cycle doesn't matter. We're not going to use the well more than it's economically usable for. The resource is going to play out long before the integrity of the well gives up. We're going to plug it, and that's it. So cheap. If cheap is considered into the design, then you know you're going to have a short life cycle. But they don't really care because it's about economics of the project. So most of the problems occur because of a failure to understand the problems in the life cycle of the well. Material failures, we're talking about differences of types of materials, quality of materials, lifespan of materials. Mechanical integrity, again, you're talking about the design of the components in the well itself, each component that goes in the well. What's its mechanical lifespan? What kind of constituents is it designed for? Conditions that it's going to encounter during the wellbore. Cement failure is a large component because it's our sealing mechanism. It's our barrier. Your casing is your barrier, mechanical barrier, and your cement is your mechanical barrier. Those are the things that keep your well where it's supposed to be and everything outside of your well. Types of cement, conditions in which you put the cement in, the mixing of the cement, all that determines the life cycle of the cement. And cement has a finite life cycle. It's not permanent. Cross flows between formations. In the water well world, you hear that as commingling of aquifers, right? We've all heard commingling. And you think, it's commingling. Okay, whatever. It's hard to see commingling, right? It's hard to see it. You got to really study and work and really understand before you can actually see commingling. If you don't see a water quality difference in a water well, then you obviously haven't commingled anything. But that's not true. Flows to surface is a really easy way of seeing that you have a problem. That's kind of how you come to most of these, is because it's flowed to surface. Something has occurred, something has happened that has brought attention to a well. By the time it's flowing to surface, your physical barriers are gone. Now there's a problem. Now somebody wants something done about it. Geologic structure. We don't know what we don't know when we don't know it, right? So you don't know you have a problem with your geology until you investigate it, until you drill it, or until you do a survey, or until you map it. And sometimes you don't know until you've already completed your projects that you have a geologic problem. Dissolution and collapse, that goes hand in hand with misunderstanding the subsurface geology. Mass transportation of sediments, again, that goes hand in hand with misunderstanding your barriers, your design, and the geology itself. Most people don't have a clue what mass transportation of sediments even represents. Degasification of reservoir fluids. And this is a really new concept that we came across. There's not a lot of published literature out there. There's some, but it's a really unique problem that like I said, I didn't know anything about this until just a few years ago. And in changes in pressure regime that you see on dilapidated systems, you see these conditions you think are dead, fields that are dead, suddenly repressurize, And now you have wells that were never designed for the pressures you're seeing suddenly expressed upon them, and then they fail. So we go back to life cycle, design and life cycle, economics of design. This particular well, literally, I just went and snagged it the other day. It's a well that's designed for short life. If you look at the original design, this is on the back reef of the Capitan. It's a Yates well, so it's into the back reef of the Capitan. They put a shallow surface casing in, set to 319 feet. They drilled through it all the way to production, all the way to the Yates, through all the back reef deposits, through the Rustler, to the Salado, Tansel, everything, and set the well into the Yates. And then he put a short cement field at the bottom. So basically, they cemented the production area as an anchor for the casing, put the casing in tension and set it in slips to the top of the hole, and left everything above the cement shoe all the way to the surface, open hole behind pipe. This is an uber typical completion of back reef wells. I mean, it's so common that you can literally just go to the Railroad Commission website, pick any of the thousands of back reef wells that are there, open it up, and see this kind of completion. This is an economic completion. Shallow cement on the surface casing, limited cement on the production casing, and nothing in between. All open hole behind pipe. So this is a really short life cycle well. The economics, they go in there, acidize it, produce it until it quits producing, then kick it off to somebody else. It's like dirty underwear. Kick it off. And then you come back and plug it. So somebody gets to the end of the life cycle of this, no longer productive. They can't kick it down the road any further. So they plug it. And a lot of times they won't plug it according to best practices. In the old days, sometimes it was just drop a telephone pole in it, cover it over. But they've since, upgraded that. Now they use cement. For instance, this particular well was completed very similar to this well, a wholly different well out of the same area. 8 5/8 casing to how deep? 62 feet. This is in the same back reef area. It doesn't even go through the Pecos Valley. It doesn't go through the Rustler. Just 62 feet. And then it's 4.5 open hole behind pipe to a cement chute. So it's all open hole behind pipe. And when they plugged it, they didn't remove any casing. And they only plugged the 4.5. They didn't perforate it. They didn't squeeze it. They shot 3 plugs right here. 20 sacks in production, 45 sacks at the bottom of the Rustler, and 5 sacks at the top. That's all that well's plugged with. And all open hole behind pipe. From the top of the Yates, through the Tansel, through the Salado, through the Rustler, through the PVA, within 30 foot of the surface. And there's a myriad of these things that are thousands and thousands of these type of wells. These are just economic constructions for the fastest rate of return. So design failure, right there. But what does that mean? What does it really mean? So you start looking at your material failure. Everybody says, well, cement, that's the best stuff there is. But during placement of cement, you have all kinds of problems that can occur. From undersaturated cement, oversaturated cement, cement that's placed in gaseous formations that have gas entrained, fluids that have solution gas with them. All these can damage your cement. Improper curing, improper mixing. These are all examples of cement that failed. These are all porous spots within the cement. Material failure of your casing. You choose cheap casing. And even the best casing has a lifespan. It all has a finite lifespan. And these are the only barriers you have within your wellbore, are your casing and your cement. That's the only barriers we have between production and your aquifers. Loss of mechanical integrity. So you've built the well, you've used the best components you have, and then the clock starts ticking. Sulfates start destroying your cement. Ions start destroying your casing. So the clock is start ticking for that timeline, that finite timeline that you can use this well. You start getting holes in the casing as you come in contact with water-bearing zones that are high in dissolved solids, high in sulfates, high in chloride. Your cement starts to dissect, starts to crack, creating micro porosity, microannular spaces. Maybe your well bore, they didn't use a scraper whenever you cemented in, and there was still mud on the interior of the well bore when they put the cement. That created a microannulus that now has dissected and is passing gas and passing fluid right through the backside of the cement, straight to the surface. Or your pipe had scale on it whenever you put it in, rust. Same thing, cement shrank back and created a microannular space between the casing and the cement. Again, you no longer have mechanical integrity. You do not have an effective seal. As you see these images here, this is actually a piece of casing that has split vertically along the original weld seam. There's seamless and welded pipe that you use in downhole tubulars. Welded pipe is historically has a problem along the weld where you have two metals welded together. That's the corrosion point where you start to see failure. And they'll split open just crack right open as it comes up the weld. This well here actually has crude oil and salt water bubbling at the top. This is a plugged well, by the way. This well was plugged, and yet their crude oil stands right there bubbling gas. This particular well here is one we saw of a section of casing completely corroded away and fluid moving at high velocities through this opening. We took a coil tubing unit down there with a video on it and watched this high velocity fluid come up the bore, out the hole, and away she went. Cross flow. So cement, that's our first barrier, our first line of defense, right? And again, these are plugged wells that we actually see salt water and crude oil standing in and bubbling. This is actively bubbling through crude oil right there. You see the bubbles? It's actively bubbling. And again, crude oil. I don't know if you can see this image here. I think you can. But this image here is of contaminated cement. The cement is infused with hydrocarbon through microporosity, through the porosity of the cement itself. It's actually just worked its way from depth up the casing and infused the actual porosity of the cement. You're thinking that's 10 to the minus 5. Well, I'm telling you, there it is. It's full of oil. Again, another well bubbling, oil and salt water and gas. So you have these same problems with cement, dissecting, degradation under assault by sulfate, contamination, undersaturated cements. In other words, cement that wasn't properly hydrated when it was put in place. It was starved when they put it in place. So the cement starts breaking down. Or cement that had too much water in it, oversaturated. It didn't set up properly. Wells that didn't have centralizers in them. In other words, keeping the casing in the center of the well. You had casing up against the formation or up against other strings of casing in the hole, creating no effective seal whatsoever. I worked on a project in Utah. And this well was 13,000 foot deep, 3 strings of casing, surface, intermediate, and production. CO2 flood field. The cement job failed on the production string. The cement job failed on the intermediate string. The cement job failed on the surface string. And CO2 drove 42 gravity oil up the backside through the cement of all these strings. It caught an angular unconformity and pushed it out into a spring. 42 gravity oil. That was hot and sweet. Highly flammable. Now this is when it starts to get interesting, because now we know we have a problem because it's flowing to surface. We can see it. People can see it. That's when they generally want you to come look and check on it. This well here, this has crude oil in the surface casing. Surface casing is 300 feet deep. This is a piece of 4.5 that's designed very similar to what we talked about before. But there's crude oil in the surface casing bubbling and coming up to surface and flowing out. That means that the plug job is completely unsatisfactory. All the plugs have failed. And it's migrating on the exterior of the production string up the backside through the open hole section behind pipe that's not sealed, passing through the rustler, passing through all your other zones that should be protected, and now rising to surface and sitting on top of your water columns. This well here is one of the imperial wells. These here, this, and this are imperial wells. They used to have containment. They lost mechanical integrity. The wells are completely destroyed. There's virtually no casing left in these wells. When we video logged them, there's nothing but Swiss cheese holes from the top all the way to as far as you go. There's no casing whatsoever. It's just destroyed, corroded relics of casing. You can even see pieces of cement, and then you see formation back behind where the cement used to be and is now gone. Same way with these. These are all the same kind of wells. This is an oil well, the orphaned oil well that started leaking out the surface casing. It started leaking 200,000 parts per million TDS water out the surface casing. Had a rupture on the seal that held the production casing to the surface casing. And at that joint, it started leaking 200,000 TDS water. This is the same place that's supposed to be protected. It's leaking. They had to go in there and replug this stuff. That is a column of water standing 15 feet in the air out of a 9 5/8 casing. It's like 4,000 gallons a minute of 300,000 TDS water. When they shut that in, it was 500 PSI with a column of brine in it. Above land surface, 500 PSI above land surface with a column of brine. 10-pound brine. That's 300,000 TDS water is about 10 pounds. It could push that column of water at that velocity, 4,000 gallons a minute. This here is 150 foot tall. And that water there was 300,000 TDS. This is not snow. This is salt. When the wind was blowing, it was automatically dissecting, and then the salt was casting down and falling out on the branches, on the ground. We were there right at the day after this happened, and you could hear this thing roar, literally roar. It's like a jet engine roaring out there. And there's a mechanic behind all of this. Those are the egregious ones. Those are the ones you see because it's visible to your eye. You can see it, you can hear it, you taste it and smell it. but it's the ones you don't see that are the most egregious. It's the subsurface crossflow button. There we go. The subsurface crossflow. And everyone wants to deny it. When you're against somebody, they say it doesn't exist. That is not a phenomenon. Fluid does not move across formations. Once you saturate, everything down below is static. Nothing moves. There's no change in head. Except that is just total fabrication. Gravity changes everything. The weight of the fluid induces its own change in head. 10-pound brine sitting on top of unsaturated fluid is heavier. It sinks. It's gravity driven, right? Like I said, this particular hole here, we had a hydrophone in the well along with the camera, and you could hear the fluid going out of this big hole in the casing. You could hear it. It rumbled like, I forget what the FS was, but it was pretty fast. It was like 40 barrels a minute. It was just getting it. This hole here we caught with the camera, and it's in a shallow water regime. It's in a shallow aquifer. Yet there's a confining unit just above this. This water is entering the wellbore, rising past the confining unit, and going out another hole above the confining unit. It's just cycling out, just like that. And this is in a shallow water well, less than 1,000 foot deep. Moving fluids, high in radium, up into another system. Think about that. And it's in a water well. You know, you're thinking, we're in the same formation, we're in the same zone. It shouldn't be a problem, right? We're in the same aquifer. It shouldn't be a problem. But you have a low conductivity seam that separates it hydraulically. And your wellbore is now the conduit in which your fluid is passing. The driller never knew. The geologists that put it together never knew. No one had ever done a survey to see if there was a change in hydraulic gradient across the bore. It's not something that you normally do, right? That's an investigation, not an installation. So this was put together back in '83. It was a seminal work. It was really eye-opening. The first time I saw it, I couldn't believe all the ways you can move fluid, move problems subsurface. I just remember thinking, wow, this guy was really smart. It's basically a roadmap of how you move fluid from one spot to another, whether it's gravity driven, pressure driven, mechanical integrity issues, flows from the surface, pressure from the surface, shot holes, core tests. The well that leaked on Highway 329, the one that had the 150-foot geyser on it, that was a core test down to the top of the Yates, 1,600 foot down to the top of the Yates. It did not penetrate an oil and gas reservoir. It penetrated to the top of the Yates. They used it to find the top of the Yates to map. That was where that well was drilled to. So whatever was driving that wasn't coming from a deep reservoir. It was coming from 1,600 feet or less. 500 PSI, 300,000 TDS water. Geologic structures. As geos, people that deal with subsurface, that's our business. That's our bag, right? Is understanding this stuff before we get involved, helping design, helping figure out economically where we're going and what we have to pass through to get there. Whenever we install wells, we run caliper logs on open hole sections, and we're looking for structure, right? The caliper is the only physical tool in the hole. How many run calipers when they assemble wells or have wireline services done? Is that part of your normal makeup? Sometimes, no times, occasionally, but it's your only physical tool, right? To give you some idea of the structure of the sidewall, of the bore itself. Pat was talking about the washout in the tuff, right? And that's the reason why you run those tools, is to see those zones of weakness. This particular section right here, we reviewed the geophysical logs for all these wells. And this row of wells here, there was a structural anomaly in the Salado. When they logged the upper section with their calipers, there was washouts in the Salado of over 30 inches in diameter in a 12 1/4 bore. Not all of them had that problem, but this row of wells did. 30-inch diameter holes through the Salado. And then we looked at the structural geology of the area, and there's a fault, a major fault that runs right through here. And I think it's more than coincidence that you see these structural anomalies within those formations are associated with stress fields with deep-seated faults. So when you design your wells, you've got to look at your areas of weakness, things that you're going to go through that are going to create problems, not just today, but problems for tomorrow. Because those are the things that are going to catch you by surprise, things you don't know, right? You don't know what you don't know when you don't know it. But the Salado, for instance, and almost all your back reef deposits within Delaware Basin, you're going to have to deal with that. You have to deal with the Salado. It's very susceptible to dissolution. We've got the Rustler sitting on top of it, which is a highly productive aquifer sitting on top of the Yates, which in most places near the reef is also productive. The Yates is just the back reef component of a very productive formation in the Capitan. This particular one is one of the holes in Imperial. These are all washout behind pipe. These are images of where the pipe used to be, and this is all holes deep into the formation, all through this section here. So now we're getting to the meat and potatoes of the ideas. So now we have a well that's gone outside of its life cycle. Now the problems are starting to materialize. And one of them we're all familiar with is dissolution collapse. It's when your zone of susceptible dissolution has now become dissolved by fluid either moving down, undersaturated fluid moving down, or undersaturated fluid rising. This particular structures are based upon undersaturated fluids moving down along the casing through failed well bores and intersecting the salts of the Salado, dissolving those salts out and transporting that fluid down under gravity. As the fluids become more weighted with the salt, they're heavier, they tend to sink, and then they migrate out through porous members below. Once the salt is gone, there's no longer enough structure to support the weight of the overburden. And the overburden starts collapsing upward, like a copla, starts collapsing upwards towards the surface until it finally breaches the surface. And that's when you have your sinklers. That's whenever the overburden is no longer capable of supporting itself and it collapses into the hole. And that is a top down, in other words, fresh water to the Salado and then out the bottom. That's a gravity driven system, all going down like a sink. Same kind of deal here. All these are gravity driven collapses. Another one is mass transportation. That's not gravity working this way like a sink. It's undersaturated fluid rising with pressure coming up. Now, this is where you have your confined aquifers. This is the problems you run into with confined aquifers versus unconfined aquifers. Unconfined aquifers want to go down. Confined aquifers want to come up. So you have undersaturated fluids from below coming in contact with your formations that are highly susceptible to dissolution. And then they find a point of exit out through the rustler. So undersaturated fluids with pressure rise become saturated, and then they shift out through the rustler or just below the rustler in the porosity just below the rustler. This is actually a seismic cross-section of a collapse, driven just like this. Fluid is rising out of the San Andreas, coming in contact with the dissolvable material out of the Salado, and then being transported out. And this whole section here is a collapse. It's visible from the surface if you drive down 1053. This is an example of that same transportation matrix. This is a spinner log that we ran in a well that had crossflow, subsurface crossflow. We have rising fluids coming up, coming in contact with our Salado, and then being transported out through porosity just below the rustler. And all the way up the hole, we're leaking through all these formations as this fluid rises up. This is 300,000 TDS fluid rising all the way to the surface. And it's coming out at about 80 gallons a minute, about 2 barrels a minute at the surface, carrying H2S, crude oil, and salt water. But not just any old salt water, 300,000 TDS. And we're losing velocity as we're coming up the hole, being less and less and less. And here is our highest velocity loss, just below the rustler. So coming up, saturating, and transporting out. Now, this is the cool part. This is what the bottle's for. Degasification of reservoir fluids. Until just a few years ago, I had no idea what that meant. Just completely no idea. As fluids are saturated, they lose their ability to solve gas in solution. The reservoirs we're dealing with, a lot of them are solution drive. They have dissolved gases in them. Or like the San Andreas has solution drive H2S. We have a lot of H2S in it, right? But there's a balance to that. It's not methane. A lot of these are not methane driven. You have H2S, but no one ever checks to see what the balance is. The balance is nitrogen, 98% nitrogen. That's what we tend to see on these type of wells, is that the balance of the gas that they're liberating is nitrogen. There's H2S in it, like this one had H2S in it. This is the one in Toya. The ones we worked on had a little bit of H2S in them. Some of them have 1% to 2% H2S in them. But as you saturate fluids, your fluids can no longer hold dissolved gas. So your undersaturated fluids that have dissolved gas in them suddenly are liberated once they become saturated with salts. It liberates the gas. So now you have gas that was once in solution, free gas, that's able to be compressed, that's able to compress, because it's a chemical reaction. And then you now have what was once dead, a motive force to move. So suddenly you have this compressible method subsurface that drives well fields that were once dead truly back to life. And over discovery pressure. Have you ever heard of a field going over discovery pressure? I haven't. What mechanism drives a dead field to have more pressure than it was when it was discovered? So this is a really smart guy, Mr. Wooler. He did a seismic survey in the Panhandle and discovered that in Salado, we have these dissolution chambers right in the base of the Salado. where nitrogen gas can accumulate. The Yates is a notorious formation to have nitrogen gas and solution gas with nitrogen. So that's a really good place to start looking, is the Yates. And once we started looking, yes, the Yates is a very good place to have solution gas, especially nitrogen solution gas. The formation is generally an unsaturated fluid or undersaturated fluid, so it has the ability to sorb substantial amounts of nitrogen. Subsurface nitrogen through the nitrification process and the anoxic reaction with subsurface shells, creating free nitrogen gas that's sorbed into the water. And once we saturate it, suddenly we have all this gas that can be liberated. So let me do a little experiment. I like this part. This is a fun one. We all agree there's pressure in the bottle, right? Come on, right?
Yeah.
Right. You heard it just release, right? For all intents and purposes, is it live or is it dead? Well, if it's not live, why isn't it jumping out of the bottle? It's just sitting there. It's not flowing out on the ground. It's virtually inert, right? Until you shake it, right? But for the most part, I mean, it's not going anywhere. Just 215 milligrams. Sorry, 15 grams, 30 grams of salt. 215 grams. Oops. Hold on. First time I did this, it caught me by surprise. So I had to come up with another method because it caught me by surprise. We all agree these things, this bottle's dead, right? For the most part. It's not jumping out on the floor. Anybody ever threw salt in their buddy's beer? Or they turned around and said, "Hey, look at her." And they turn around and you take the salt shaker and throw it in the beer and the bubbles all over the floor. Anybody?
Yes,
No takers?
absolutely.
I asked a bunch of attorneys that. And they were like, "No, never in my life. I don't drink alcohol." So what's he going to do? Why is it going to blow up? Well, yeah, well, it'll increase by the volume of what we put in there, right? Which is just a little bit of. But salt is a funny thing, right? As soon as you put salt in there, it not only does it liberate the gas, it shoots the water up into the balloon. Yeah. How much more volume is in the balloon than what was in the bottle? And why? Why didn't that jump out all over the ground and throw itself all over the floor when I took this lid off? Where was the energy? This is energy. This is stored energy, is it not? It's definitely compressed. That's why we got a balloon. Be careful over here. First time I did it, it caught me off guard. It's not going to do it again. Look at the volume exchange, right? Where did this come from? Where did it come from? It came out of solution, but look at the volume. The volume compared to what was in here at the same atmosphere. And suddenly you have a chemical reaction. Now you've liberated all the gas that was in solution. And this becomes a drive mechanism. And there was enough drive mechanism to elevate it at least a foot. With just that little bit of salt in that bottle, it elevated all that fluid from the bottle into this balloon over a foot. So that's a drive. So we took this well field that we're working on. It's a problem field. We put well heads on them. And then we put gauges on them and loggers. And then we started logging over time these wells that were problematic. And they said, they're not a problem. It's not a problem. They're not working together. There's no uniform theory here. There's nothing going on, nothing to see. And look at these guys all working together, building pressure over time. Same concept. These are wells that are several miles apart on the same property. And once we sealed them up, all started building pressure uniformly. Nitrogen. So this is a drive mechanism to move fluid vertical through your well bores back into your aquifers. And we're not talking about light water. We're talking 300,000 TDS fluid. That's the reason why it no longer has gas in it, because the salt has driven the gas out. It came to it loaded with gas, became saturated with salts, liberated the gas, become a drive mechanism, and forces it to surface. That's why those wells go as they're bleeding off the gas that's driving them, just like an air compressor unloading a well. How many drillers in here who sat on the rig and been blown off the step by the water coming out of the hole? It's the same mechanism. Compressed air, compressed gas, rising fluid trapped on top of it. Think about it, Tom. Yeah, this is 8 gravity crude oil. Weathered, viscous 8 gravity crude oil. We did a survey on this, an investigation, turned it in the road commission. They said, I don't know what that is. Not our fault, not our baby. Thank y'all.